Hi, my name is Alex Castaneda. I'm here an FIU Capstone student presenting for my team. We are a part of Spring 2024 Capstone. Our project is called Geometric Visualization Tool, and the team members are me, Alex, Anthony Thompson, Jinpan Zhang, Alex Navarez, and Joseph Mejia. Our product owner is Professor Antonio Hernandez, and our capstone professor is Mr. Masad Sajidi. Our problem description regards introducing the need for our project. So, geometric visualization tool is what we made for this capstone project, with specifically in mind in the instance of the FIU class, computational geometry. Students often struggle in this class in developing, and we try to fill that need with our tool. So, while again it has a specific instance in mind, the general purpose is beyond that to serve outside of the students, the teachers, and also developers, whether it's a student outside of the class or doing group work. And again, using geometric structures visualization with Java. The project tries to achieve this purpose by only focusing on the implementation of the most basic because that's the foundation. These basic geometric objects and data structures and algorithms have to be scaled up after because they have so many instances. For example, we built out points, lines, rays, triangles, um, but beyond that, these have specific instances like weighted points, which the complexity scales up, or an algorithm which has rays throughout the object so that it is testing the vertical of the object. Again, simplicity foundation was made first. Our visualization tool addresses a current shortage of geometric algorithms in Java. So this tool helps to fill that gap to provide more efficient development and easier time for visualization, since Java is really lacking on this side compared to C++. We tried to solve this problem by the tools that set itself apart by being an abstract framework, utilizing its full capabilities of two external libraries that's in it, the Seagull library and a Java private library called JGEM. JGEM is just a standardization of the testing classes and the window displaying for graphing. And Seagull Library is a powerful public C++ library that is used for geometric data structures. So, with these tools' functionalities, currently our tool revolves around aiding, designing, implementing, and testing geometric data structures that a student would struggle with on the Java side. With Seagull's integration used and its robust capabilities, and Java's strength in the scholastic setting by students, it becomes a much easier time for everybody to develop, and this becomes a quick and powerful resource. As well, we lower the demand or the need for Seagull library, which is very hard to install and have running and maintain by the looping that we did in the system, meaning that always it could be refined the data through a TXT file, and only one group member needs Seagull to make the C++ text files needed for the rest of the group. So we had three main goals, which was in this capstone semester building out the initial abstract framework with the goal of adding more graphing collections. We also, in mind, developed with simplicity scaling in mind, of course, again, repeating the most simple geometric data structures like Voronoi diagrams, triangulation diagrams, and later on, by future teams, they will include the more complex ones. As well as we made a complete and sound system architecture with the looping design importing and exports on both sides, meaning refining is possible throughout the abstract framework. So our user stories were split up between what language they were being done in the Java side or the C++ side. In the Java side, we built out the framework with simple methods or functions to add these graphing collections of geometric objects. We also formatted and standardized all of the toString objects for even between different shapes, lines, rays, and later on it needed to be done to be building blocks for Voronoi and Delaney triangulations. We created a simple parser in Java for the appropriate imports coming from C++ exports, in which, again, all the relevant info is standardized and broken down in an orderly way from the TXT file. We also implemented the export and import for the Java side, of course, for again, refining always being possible. We did this for C++ as well. Again, it's a loop and it has import and export aspects in both sides. We utilize computational geometry capabilities from Siegel to visualize geometric objects. We created simple program exercises to implement the geometric objects on the C++ side of Voronoi, diagram, and bare bones. We also reformatted and broke down our C++ code base that we had developed halfway to make it easier for other users to run. So, from what we had previously, we made a C++ architecture of .h, .cpp file, and main file for the right and appropriate way that makes it easiest for somebody to run and join us. These are the technologies that we leveraged. So there's the Seagull library, a powerful public computational geometry algorithms library, which gives us reliable access to these data structures and the right computations and calculations in arithmetic. We use an IntelliJ, which was the IDE for our entire Java code base in which testing and graphing was done. Also, with IntelliJ, we were able to implement the JGeome library. On the C++ we used, which was the language for half our code base for our abstract framework, with a main.cpp geo2util.cpp and geo2util.h file. For the testing of the export side, we also use this. We use Visual Studio Code IDE for the C++ side and to have the relevant libraries and implementations. And Java was again half of our language used to write the abstract framework tool with files of file util, test file read, tester classes that we made as well. So right here you see the object design diagram, which is our UML for the C++ side. And you see the dependencies here that main.cpp has to Geo2 util interface, to the Seagull library, and that the interface has dependencies in enumerations and special relationships with color. As well, here you see the UML for the Java side. We see test file read, we see file util. We see file util has no public variables. It uses the ones from the package of JGeome for smooth transition. But again, we see all these important functions of parsing all these different types of objects and also exporting all these different types of objects and also storing all this important data. Here we see the test file read had all private variables such as width, height, the array, and the application, which is all used in graphing. Here we see the system architecture for our project. This is used here as a loop. We see here the spitting it out from export to import and vice versa on each side from C++ to Java or vice versa from Java to C++ and the use of each library in this and what it's outputting and what it's importing. Here we have a use case diagram with all the relevant actors. All the relevant actors can use the first use case, but what really becomes important is that this is the tool system and how these use cases interact from first and second. So we see the abstract framework can add collections, and also that the abstract framework can get objects from Seagull. And then from that, it could either be spit out to be exported after using Seagull, or after adding the collection, it could be visualized and then exported again. And we see also the imports that's done. We see the right process and flow of the data here. Here we see even more clearly the system design flow. Here we see from Seagull the imported and exported TXT files that are then imported into Java. And then we see the data reading as well by whatever type of compiler you have, the parsing, either single points or multiple points, or either single line segments or multiple line segments, which then extend themselves and scale themselves in scalability in data visualization to be geometric objects such as circle, triangle, rectangle, polygon, and then later on, all those become the more complex in scale Voronoi diagrams and Delaney triangulation data structures. Here we see an output of the ray, multiple different rays, multiple different points, connected and not connected. We see multiple different circles. We see here the color, how much it's important, how much you could play with it, the boundary color, the interior color, the points. Also here we see the Voronoi diagram, the most complex thing made. We see here how good the Voronoi diagram is in finding where there is a lack of ATMs on campus on the left side. And here in the Voronoi diagram of parking, we see what it is closest to a student or a person on campus based off where they are. Here we summarize in this project, it gave us the opportunity to fully learn computational geometry, even when some of us didn't have a background. And the ones that did, like Anthony, were able to even extend their background. We, from the ground up, built documentation, tester classes, architecture for the system in C++ and Java, diagrams, and also the implementation of export and importing capabilities on both sides of the code base. We extended and refined our knowledge for Java graphics and beyond, and also CL. With the help of our product owner, Mr. Hernandez, we were given both freedom and guidance in the development phase by creating our own test classes to fully learn the components and capabilities of this tool has right now. With Jinpan's leadership in C++, Anthony's in Java importing, and also my guidance regarding the system design, we feel like we have left off something great for further students to build up.